There's so much more to mathematics than just doing calculations and solving problems. Math is also about communicating ideas and making arguments based on sound logical reasoning. In this lesson, we'll see how calculus gives us some valuable tools to do exactly that. I haven't told many people this, but I can read minds. And I'm going to try to do it right now. Grab a sheet of paper or open up your favorite word processor. What I'm going to do is ask you to write something down, and I want you to write down the first example that comes to your head as quickly as possible. No curating to try to impress me. I really want your gut instinct here. Okay, ready? Here's what I want you to do. I want you to write down the first theorem that comes to your head. If the theorem has a name, write down the name of the theorem, and also write down what the theorem says to the best of your ability, as best as you can remember. Pause if you need some more time to do this. Don't worry, I'll still be here. Okay, got your theorem? All right, let's see if I can do this. It's been a while, I'm a little out of practice. Okay, yes, I'm starting to get a picture now. Literally a picture, so probably something to do with geometry. And it seems kind of pointy, so maybe something involving triangles. And then as for what the theorem says, I feel like I'm seeing the alphabet, but not the whole alphabet, just the beginning. Just the ABCs. ABC, ABC. Okay, I think I've got it. All right, here's my prediction. You wrote down the Pythagorean theorem. And as for what it says, you wrote down a squared plus b squared equals c squared. Did I get it right? Okay, I'll admit, while I'd like to believe that I have extrasensory perception, the reality is that the Pythagorean theorem is often the only theorem that most students learn in high school, maybe with the fundamental theorem of algebra being a close second. Now, to be fair, the Pythagorean theorem is pretty famous. It's been around for quite a while. In fact, there's evidence that the ancient Babylonians knew about it and proved it 1,000 years before Pythagoras was even born. And it's been proven hundreds of times, each with a different flavor, some geometric, some algebraic. But while lots of people know the Pythagorean theorem by name, a lot of people get the theorem itself wrong. If you wrote down a squared plus b squared equals c squared, that's actually not quite correct. Don't believe me? Look at these two pictures. So, do you see the issue? Okay, that was a really bad one. I'll take responsibility for that. But anyway, those symbols A, B, and C are meaningless on their own until we know what they're supposed to represent. A, B, and C are the lengths of the sides of a right triangle. Specifically, C is the length of the hypotenuse, the longest side, the one across from the right angle. Remember the Charlie Brown cartoons and the sound that the adults make when they're talking? Wah, 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 wah. Well, lots of theorems are written as if this and this, then formula. But what a lot of students seem to hear is wah, 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 formula. And if you're not careful with your conditions under which the formula applies, you can end up making mistakes like the ones that we saw, blindly juggling symbols around on the page without remembering what they're supposed to mean. What we're going to do now is look at some theorems that let us describe the behavior of certain functions using limits. And I hope that what we've just talked about shows why you need to pay close attention, not just to the result, but also the conditions under which you can use that result. The first theorem we're going to look at tells us how we can use inequalities to compute certain limits. Here's an example. The limit as x approaches 0 of x squared times the sine of 1 over x. How could we compute this limit? Well, a good place to start is usually a graph. Yikes, that's a weird graph. As x gets closer and closer to 0, the function wiggles faster and faster and faster, just like those oscillating discontinuities we've seen before. But something's kind of different about this one, because as the oscillations get faster, they also seem to be shrinking down to 0. so it appears that the limit is 0. But how do we know for sure? We could try to use our limit laws to split this up into a product of two limits, seeing what happens separately when x squared and sine of 1 over x approach 0. That's easy enough for x squared, but for sine of 1 over x, that limit doesn't exist because we have an oscillating discontinuity. So, unfortunately, that won't work. But consider this a second. No matter what x is, sine of 1 over x is always between -1 and 1. That's the range of the sine function. And if we multiply this inequality through by x squared, then we preserve the inequalities, since x squared is always either positive or 0. So therefore, x squared times sine of 1 over x is always bounded above by x squared and below by -x squared. How does that help us? Well, as x approaches 0, x squared also approaches 0, and so does -x squared. That doesn't give our function x squared times sine of 1 over x much wiggle room. Since the functions bounding it both go to 0, it's squeezed in between them, so it's forced to also go to 0. So the limit is 0. This result is an example of something called the squeeze theorem. Here's what it says in general. Suppose we have three functions f, g, and h. And suppose that g of x is always between f of x and h of x for any value of x close to some number a. If the outside functions f and h go to the same limit as x approaches a, then g is squeezed in between them and also forced to go to the same limit. The squeeze theorem can be useful in situations where your usual limit techniques don't quite work. For example, think of the limit of sine of x over x as x approaches 0, the one we saw in our first lesson on limits. We saw numerically that it seemed to approach 1, but we never really proved for sure that the limit was 1. But by making a diagram of an angle theta projected onto the unit circle, we can see that the arc along the circumference also has a length of theta. That's due to the definition of what radians are. And also notice that when theta is small, close to 0, sine of theta is always just a little smaller than theta, and tangent theta is always a little bigger. From there, a little algebra shows that sine theta over theta can be squeezed between cosine theta and 1. And since both of those approach a limit of 1, when theta approaches 0, sine theta over theta is also forced to approach 1. It has nowhere to go. That's the squeeze theorem in action. When we studied linear approximation, we mentioned that there are a lot of questions out there that algebra just can't answer, where you need a computer to find an approximate solution. Here's one of them. Is there a number that is its own cosine? In other words, is there a solution to the equation cosine of x equals x? You can try to solve this algebraically, but you won't get anywhere. Unfortunately, nothing will work to get x by itself. So it would seem we're out of luck. But take a look at this. Say we get everything over to one side, like we often do with equations, and call that one side f of x. So now we've turned our question into finding where f of x, cosine x minus x, is equal to 0. Now, if we plug in x equals 0, we'll get cosine of 0 minus 0, which comes out to 1. But if we plug in pi over 2 for x, we get cosine of pi over 2 minus pi over 2, which comes out to negative pi over 2, about negative 1.57 or so. So f of 0 is positive, while f of pi over 2 is negative. Doesn't it seem like somewhere between 0 and pi over 2, there should be a place where f has to hit 0? That's a good intuition to have, but think, what if f just skips over 0 without ever actually equaling 0? Could that happen? Well, maybe with some functions, but if the function is continuous, then that shouldn't happen. And that's what we call the intermediate value theorem, or IVT for short. The IVT essentially says that continuous functions can't skip values. At least that's the gist. But we can get a little more specific. More precisely, if a function f is continuous on a closed interval from a to b, that means it's including the endpoints, then it has to hit every number between f of a and f of b at least once. But what does that mean, to hit every number? Well, put even more precisely, if we pick some number m between f of a and f of b, then there has to be some value c between a and b for which f of c equals m. Notice what we've done here is start with a basic idea. Continuous functions can't skip values, and little by little made it more precise. That's kind of what mathematicians do. We take some sort of key intuition and encode it in mathematical language and symbols, so we can use mathematical tools. But be careful that you don't get so caught up in the mathematical symbols that you forget the intuitive idea that those symbols are supposed to represent in the first place. So here's how we use the intermediate value theorem for our equation. Remember that f of x equals cosine x minus x. Since cosine x and x are both continuous functions, so is their difference. So that means that f is certainly continuous on the closed interval from 0 to pi over 2. And then notice that f of 0 is a positive number, and f of pi over 2 is a negative number. So then, since 0 is between f of 0 and f of pi over 2, by the intermediate value theorem, there must be some value c between 0 and pi over 2, so that f of c does come out to 0. So our equation, cosine x equals x, must have a solution somewhere between those two numbers. By the way, this is a template you can often use for arguments where you use some theorem. First, show that the conditions for the theorem have been met, giving specific evidence. Second, cite the name of the theorem you're using. And finally, draw the relevant conclusion, and if necessary, tie it back to the original problem you were trying to solve. If you follow this template, you'll usually have a good solid argument. Now, a few words of caution. First of all, it's important that all of the conditions of the theorem be met, or your conclusion may or may not be true. Like if your function wasn't continuous on the entirety of the closed interval, then it may or may not skip over certain values. Or if the value you're looking for isn't between f of a and f of b, then the function may hit it, or it may not. And second of all, the intermediate value theorem tells you that the point you're looking for exists, but it doesn't actually tell you where or how to find it. That requires a bit more work, though that's exactly the sort of thing that computers were built to help with. In this case, the value of x, for which cosine of x equals x, turns out to be about 0.739. And in fact, the way your computer finds that value depends on the intermediate value theorem in order to work in the first place. Next, think back to when we did optimization, and we looked at trying to find the minimum surface area of a soda can with a volume of 12 ounces, or about 21.65628 cubic inches. As a reminder, we found the surface area as a function of its radius. S equals 2 times pi r squared plus 2 times the volume times r to the negative 1. We found that the minimum area was about 43.01 square inches, which happens when the radius is about 1.51 inches. But what if we turn this on its head and tried to find the maximum surface area of the can? Well, if you graph that surface area function we found, you see pretty quickly that, well, there is no maximum. As the radius approaches 0, that surface area rockets off toward infinity. But in real life, there's probably no way we could have an infinite surface area, at least as far as I know of, because we're bounded by real-world constraints. And remember that when we restricted the radius to a certain range of values, a closed interval in fact, we were guaranteed to hit a maximum and minimum value somewhere in that interval. If the radius has to be, say, between 1 inch and 2 inches, then the absolute maximum surface area is about 49.60 square inches, which happens at the boundary point, r equals 1. But the absolute minimum surface area is still about 43.01 square inches, which happens at the critical point, r equals about 1.511. So this is actually demonstrating another valuable theorem, the extreme value theorem, or EVT for short. The EVT has a similar flavor to the IVT, but with a different conclusion. It says that if a function is continuous on a closed interval, then it has to reach an absolute maximum and an absolute minimum somewhere on that interval. Once again, it doesn't tell us where those extreme values happen. We'd have to do some more work to find them, since they may happen at either a critical point or a boundary point, as you now know how to do. All the extreme value theorem does is guarantee that the maximum and minimum values exist. So anytime you're solving an optimization problem involving a continuous function, and your variable is constrained to a closed interval, you can rest assured that you'll find your optimum solution. Guaranteed, thanks to the extreme value theorem. Here's a scenario. Imagine a long straight road with a bad speeding problem. The posted speed limit is 35 miles per hour, but drivers regularly go way faster, and that's putting people in danger. So you, being in charge of the Department of Public Safety, put cameras along the road to try to deter speeders. You see some reduction in speeding, but some drivers have started being a little sneaky. They slow down to 35 miles per hour by each of the cameras, but then speed right back up for the stretches between the cameras. Is there anything you can do about it? Turns out, calculus comes to the rescue once again, with our last theorem, the mean value theorem, or MVT for short. Here's what it says. Say you have a function f, which is continuous on the closed interval from a to b, and differentiable on the open interval from a to b. That means it may not be differentiable at the endpoints, but between them, the curve has to be smooth in a sense. Then, if it meets those conditions, there must be some point C between A and B where the slope of the tangent line, the derivative, f prime of c, equals the slope of the secant line connecting the two endpoints. Put another way, there must be some point where the instantaneous rate of change equals the average rate of change. Take a moment to digest that if you need to, both the conditions and the conclusion. Then move on when you're ready. Okay, how does this theorem help us catch the speeders? Suppose we have two cameras that are 4 miles apart. A car passes the first camera, and then 5 minutes later, it passes the second camera. Both times it's going 35 miles per hour. But let's see if the MVT can tell us what really happened. We know the car traveled 4 miles in 5 minutes, which is 1/12 of an hour. So that means that the average velocity of the car is 4 divided by 1/12, or 48 miles per hour. But that's just the average velocity. Now, the position of the car is certainly a continuous function of time. Otherwise, it would be able to instantly teleport from one place to another. We haven't invented that technology yet. And it's also reasonable to assume the position function is differentiable as well. When you're driving a car, you don't suddenly change velocity at any point, but rather you gradually accelerate, speeding up or slowing down as needed. So, since the position function is continuous and differentiable, by the mean value theorem, there must be some point in time at which the car is moving at an instantaneous velocity of 48 miles per hour, which means the car has to have been speeding. We don't know when exactly this happened. Once again, the MVT doesn't find where this instantaneous rate of change matches the average rate of change, but it does guarantee that it had to happen at some point. Caught in the act by calculus. So all in all, we've seen 4 valuable theorems: the squeeze theorem, the intermediate value theorem, the extreme value theorem, and the mean value theorem. Using these theorems, we can guarantee certain behavior in functions, as long as we can show evidence that the various conditions involving limits, continuity, and in the last case differentiability have been met. I hope this has given you a better idea of what mathematical reasoning should sound like. We have something we want to show is true, and using the information we know, we piece things together, presenting it in a logical way, leading to our ultimate conclusion, proving it beyond a shadow of a doubt. And that's going to come in handy for our next and final lesson, in which we'll bring everything we've been doing together and prove the fundamental theorem of calculus.